Today we're going to talk about solubility and the impact that intermolecular forces has on the solubility of any solution. So looking at seawater, it is a solution. It is composed of a homogeneous mixture of, say, two or more substances or components. And the majority of seawater, the majority component is water, and that is what we call the solvent. And the minority component is called the solute, which is the sodium ions, the chloride ions, and any other ions in solution. So when you look at an aqueous solution, water is the solvent, and a solid or a liquid, or could even be a gas, is the. So when we look at a solution and we talk about the solubility of that solution, what we really are talking about is the amount of a substance that will dissolve in a given amount of solvent. And as we go through, we are going to look at how intermolecular forces affect solubility. Now, in a solution in which there were no intermolecular forces, what you would expect to see is that two substances would spontaneously mix to form a homogeneous solution. Now, if you recall, there are various types of intermolecular forces that have to be overcome when you are in solution. There are dispersion forces, there are dipole-dipole interactions, there is hydrogen bond, and there are ion-dipole interactions that a solution must overcome in order for it to be soluble. So as we go through, we're going to look at what it takes for solubility to take place. Now imagine a solution which contains both solute and solvent. And here we are talking about the solvent particles in blue and the solute particles in red. Now there are lots of interactions going on in this molecule. The solvent and the solute particles are interacting, the solvent particles are interacting with themselves, and the solute particles are also interacting with each other. If you look at the relative interactions to determine whether a solution will form, if the solute-solvent interactions are greater than the solvent-solvent interaction and the solute-solute interactions, then you will see that a solution will be formed. If the solute-solute interactions are equal to the solvent-solvent interactions, as well as the solute-solute interactions, then a solution will also be formed. If the solvent-solute interactions are less than the solvent-solvent interactions and the solute-solute interactions, the possibility exists that a solution will form dependent on the disparity that exists between the interactions. Now, concentration is a measure of the amount of solute in a given amount of solution, or occasionally solvent. And concentration can be measured by molarity, which is the amount of solute in moles over the volume of solution. We can also describe concentration in mole percent, which is the amount of solute, divided by the total amount of solute and solvent multiplied by a factor of 100. You can also describe something by parts per mass. If you were talking by concentration, it would be the mass of the solute over the mass of the solution multiplied by the multiplication factor of 100. Now, if you are talking about parts per million, that multiplication factor becomes 10 to the 6th. And if you're talking about parts per billion, that multiplication factor that you are going to use is going to be 10 to the 9th. And this is how you determine parts per million versus parts per billion. Now, concentration can be measured in the laboratory using a volumetric flask. In the laboratory, say for sodium chloride, if you're making a 1 molar solution, you're going to weigh out 1 mole of sodium chloride, which is 58.4 grams, into a volumetric flask. Once that is weighed, then you will add water to the to the sodium chloride, and you add it to a specific marker on that volumetric flask. You mix it, and that solution becomes a 1 molar solution. Osmosis is the movement of water molecules from a region of low concentration to one of high concentration through a semipermeable membrane. The amount of pressure needed to keep osmotic flow from taking place is called the osmotic pressure. And that's usually measured as the difference in height when you are measuring using a U-tube. Osmosis is very important in the biological environment. An isoosmotic solution is a solution that has the same osmotic pressure as the solution inside the cell. As a result, if a cell is placed in such a solution, there is no net flow of water in or out of the cell. On the other hand, a hyperosmotic solution is one that has a higher osmotic pressure than the pressure of the solution inside the cell. Because of this, there will be a net flow of water molecules from inside the cell to the outside of the cell. As a result, the cell will shrivel. A hypoosmotic solution has a lower osmotic pressure and causes the cell to swell.